Welcome to True Projects. In this video, we are going to explain about the project entitled as a quantum enhanced artificial neural network model for efficient medical image compression. So before getting into the video, let me give you the brief description about the project. This title refers to a hybrid approach that combines quantum computing techniques with artificial neural networks to compress medical images efficiently. The model uses quantum principles to extract compact and informative features while preserving critical diagnostic details. As a result, it reduces storage and transmission requirements without significantly compressing image quality. Coming to the abstract, this paper addresses the challenge of efficiently storing and transmitting medical images, which are typically large in size and demand high storage and bandwidth. Conventional image compression techniques can reduce file size, but they often compress important diagnostic details, making them unsuitable for medical use. To overcome this limitation, the proposed approach introduces a quantum enhanced artificial neural network that integrates quantum feature extraction with classical neural networks. In this method, medical images are first standardized and converted into quantum states, where quantum principles such as superposition and entanglement help extract rich and compact feature representations. These quantum enhanced features are then used by a classical neural network to compress and reconstruct the image efficiently. Experimental evaluation on brain CT, brain MRI, and COVID chest X ray datasets shows that the QANN approach produces high quality reconstructed images while significantly reducing storage requirements. The improved performance is validated using SSIM and PSNR metrics, demonstrating better image fidelity and superior compression efficiency compared to traditional models. Coming to the existing system, the existing medical image compression systems primarily rely on classical compression algorithms to reduce image size for efficient storage and faster data transmission. While these methods are effective in minimizing file size, they often result in a loss of image quality, which can affect the visibility of important diagnostic details. Techniques such as deep convolutional autoencoders are commonly used and can perform compression to a certain extent, but they struggle with highly complex medical images and may degrade structural information during reconstruction. Additionally, training these models on large and diverse datasets require high computational power and long training times. As a result, existing systems are less suitable for real-time medical applications like telemedicine, where both high image quality and fast processing are critical. Coming to the proposed system or base paper work, the proposed system presents a quantum enhanced artificial neural network approach for effective medical image compression by integrating quantum computing concepts with classical neural networks. Initially, medical images undergo classical pre processing to standardize and prepare the data for quantum encoding. The processed data is then transformed into quantum states using unitary operations, allowing it to be handled in the quantum domain by exploiting quantum properties such as superposition, entanglement, and parallelism. The QANN extract meaningful and compact feature representations while removing redundant information. These quantum enhanced features are passed to a classical neural networks which reconstructs the comparison images with minimal loss of critical diagnostic details. Experimental results demonstrate that the proposed system achieves higher image quality reflected by improved PSNR and SSIM values, along with significant storage reduction across MRI, X-rays, and CT scan dataset. This hybrid quantum classical framework, implemented using Qiskit library, offers efficient storage, faster transmission, and enhanced compression performance, making it well suitable for bandwidth constrained medical applications such as telemedicine. Coming to the dataset, the COVID-19 chest X-ray image repository is a publicly available dataset consisting of chest radiography images collected from confirmed COVID-19 positive patients across multiple online sources. The dataset primarily includes frontal chest X-ray images in anterior posterior and posterior anterior views packed as a zip archive containing approximate 900 images. In addition, a CSV metadata file provides detailed information for 452 of these images, such as patient and imaging details. While all images corresponded to COVID 19 cases, some may represent pediatric patients or early stage of infection where visible abnormalities are minimal or absent. Release under the Creative Commons attributes. This dataset is well suited for research purpose including medical image analysis, machine learning, and deep learning model training related to COVID-19 diagnosis. Coming to the novelty or extension or enhancement or improvement. So, firstly, although the QANN based compression approach significantly reduces image size while maintaining diagnostic quality, achieving a perfect structural similarity index is not feasible with comparison alone. To further improve the visual quality of reconstructed images, a super resolution algorithm is integrated as an enhancement to the system. This extension refines the constructed images by increasing resolution and restoring fine details that may be lost during compression. The SR algorithm operates with minimal additional computational overhead, making it efficient for practical use. By combining QANN based compression with super resolution enhancement, the proposed system delivers high quality medical images with improved clarity, ensuring reliable diagnostic while remaining suitable for real time and bandwidth sensitive medical applications. Along with that, as an extension, a Flask framework is used to develop a user friendly interface that allows users to provide input data for prediction. The input is pre processed and passed to the trained model based on the dataset. The predicted results are then displayed to the front end interface, making the system easy to access and usable. Coming to the workflow, firstly, we need to set up an library imports. The first module focuses on preparing the environmental for the notebook execution. Warnings are suppressed to clear output and all necessary libraries are imported. This includes quantum computing tools, image processing libraries such as OpenCV and Pillow, numerical computation libraries like NumPy, visualization libraries such as Matplotlib and Seaborn, and deep learning framework like Keras. Additional utilities for model management, training, and evaluation are also included in this model. Next, evaluation metrics. This module defines functions to evaluate the quality of compressed and reconstructed images. The structural similarity index is calculated to access how closely the reconstructed image resembles the original in terms of structural and details. The peak signal to noise ratio measures the amount of noise or distortion introduced during compression. Together, these metrics provide a quantitative assessment of the performance of the comparison and reconstruction process. Next, quantum feature extraction. The pre-trained quantum enhanced artificial neural network is loaded using the QANN dot load QANN function. The QANN model converts classical image data into quantum states and processes them using quantum principles such as superposition and entanglement. This module is responsible for extracting quantum enhanced feature vectors for medical images, which retrain critical diagnostic information while reducing redundancy. Next, data pre-processing. This module handles preparing the input images for both quantum and classical processing. It involves standardized image data, resizing images to a constrained format, normalizing pixel values, and converting images into font suitable for quantum encoding and neural network input. It may also include splitting the dataset into training and testing subsets to facilitate model training and validation. Next, classical neural network setup. Once quantum enhanced features are extracted, this module defines the classical neural network architecture, typically a convolutional autoencoder or similar model for image compression and reconstruction. The extracted quantum features are fed into the network to compress the image representation. During reconstruction, the network decodes the compressed features back into image form, allowing to compression with the original usage SSIM and PSNR metrics. Next, model training and evaluation. This module trains the classical neural network using the quantum enhanced features. Callbacks such as model checkpoints may be used to save the best performing model. After training, the model's performance is evaluated on testing images with reconstructed image compared against the original image using SSIM and PSNR. This module ensures the effectiveness of the QANN based compression framework. Coming to the front end of the application is built using Flask framework, providing a user-friendly web interface. It includes user registration and logging functionalities supported by an SQLite database. For secure credential management, users can submit input through the interface, which are then pre-processed before being fed into the trained model for prediction. The resulting output is displayed directly on the front end, allowing users to easily view and interrupt the model predictions. Coming to the requirements, we have both hardware and software requirements. Hardware requirements consisting of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework is Python 3.7.2, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap. 4. To execute this project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the execution of the project, firstly, you need to copy the path of the code folder from the address bar of the file explorer. Then, open command prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the command prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it into any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front end built using Flask framework. In this page, we have home button, login button, and get started button. Firstly, click on get started button so that create account will be opened, where you need to enter the details and create an account for user authentication like username, full name, email ID, contact number, and a strong password. Then click on create an account so that all the given details are stored in signup.db and login.html will be opened, where you need to access the application by entering username and password. Then click on sign in. The prediction page has been displayed. In this page, we have prediction button, graphs button, notebook button, and logout button. Firstly, click on prediction button so that the prediction form will be opened, where you need to upload the medical image for compression. Firstly, upload the file from the code folder from the test images. Choose any one image, then click on open. The image has been uploaded, then click on process image with QANN. So the given input image is pre-processed and the output will be displayed like about the results. This is the original image, this is a decompressed image, and this is super resolution image. We have the information related original image, decompressed image, super resolution image, and we have process another image. When you click on this, again the form will be open where you can upload another image. Here we have print the result so that the results will be printed. Now click on graphs button so that the graphical representations present in the project will be opened. Let us check one by one. First, we have proposed QANN training versus validation loss graph. The graph shows the training and validation loss of the proposed QANN model over multiple epochs. Both losses decreases rapidly in the initial epoch, indicating effective learning. Then they stabilize at low values and closes follow each other, suggesting good convergence and minimal overfitting. Next, we have compression storage size comparison graph. This graph compares storage size before and after compression using the different techniques. The original data requires very large storage, while the existing DCAE significantly reduces the size. The proposed QANN achieves the smallest storage size, demonstrating superior compression efficiency. Next, we have SSIM comparison graph. The graph compares the structural similarity index of two methods, existing DCAE and the proposed QANN. The existing DCAE achieves an SSIM of 0.61%, while the proposed QANN reaches a higher value of 0.77%. This indicates that the proposed QANN produces images with better structural similarity to the reference image. Next, we have PSNR-DB compression graph. The graph compares the PSNR values of the existing DCAE and the proposed QANN methods. Both techniques achieve very similar PSNR values, with existing DCAE at 0.30 dB and proposed QANN at 0.29 dB. This indicates that image reconstruction quality is compatible for both methods in terms of noise levels. And next we have all algorithm performance comparison graph. The graph compares the performance of existing DCAE and proposed QANN using PSNR and SSIM metrics. Both methods show nearly identical PSNR values, indicating similar noise reconstruction performance. However, the proposed QANN achieves a significantly higher SSIM, reflecting better structural image quality. And then click on logout. So finally, this project demonstrates that a quantum enhanced artificial neural network is an effective solution for medical image compression, achieving higher compression rates while preserving efficient Diagnostic information. By integrating quantum features extraction with classical neural networks, the system improves image quality and reflected into SSIM and PSNR metrics. This approach significantly reduces storage and bandwidth requirements, making it suitable for real-time medical applications such as telemedicines. So this is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.